A very good morning. Today, we will go on to a new, very important topic in theory of computation known as formal languages. You all might be very familiar about what is a language. For example, I can say that English is a language, Hindi is a language, Malayalam is a language. Okay. Or if you talk in computer terms, you can say C is a language. We even have a language called CPP or Java and so on. Now, today what we will see is what do you mean by a formal language? Now, I have an example over here. You can see a figure on your right, a car. A boy is riding a car. Now, when you talk about that particular sentence in English, you say, it is a car, or I can say, this is a car. Okay, so that is how I write it. I write it like, this is a car. So this I can say it is a formal language. Now, why do I say it is a formal language? I say it is a formal language because, I do have a concept called words over here, or I can say this whole thing is called a sentence. A sentence is nothing but a combination of words. I do have a four words over here. This is a word, if is a word, a is a word, and car is a word. Okay. Now, a formal language, it will consist of words together, which will form a sentence. Okay. So how do you form a word? We saw earlier, you form a sentence with words, or in other terms, I can say it is even a string. So we very clearly know that sentence is nothing but a combination of words or strings. Now, how do you make a word called this? Let's talk about the word called this, THIS. Now, it has something called letters. T is a letter, capital T is a letter, H is a letter, I and S. All these are letters. Now, I cannot have a word in English like this. Like, imagine I can, it doesn't make a meaning. It doesn't give sense. Instead of I do have another symbol over here, which, with respect to the English language, I cannot recognize this to be a word. Now, when you write a sentence or a word like this, a word or a string, it can have something called letters. Now, these letters are nothing but they come from something called alphabets. Now, in English, when I'm talking about a formal language called English, I can have a set of alphabets. Okay, I can have alphabets. It can range from A to Z, capital A to Z, and small a to Z. These are my set of alphabets. Okay. Now, the letter is nothing but each and individual component of my alphabet. For example, capital A is a letter, capital B is a letter, C is a letter, etc., 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 up till capital Z. All of these, I say them to be letters. And the whole set of letters, I say they are alphabets. So letters, they are subsets, or they are components of your alphabets. Okay. So when I come back to this sentence, I say, this is a car. The whole thing is a sentence. When I talk about words, this, comma, is, comma, a, comma, car, all of those are words or strings. When I talk about letters, each and everything, T, H, I is, all those are letters, and they come from my set called alphabet. I do have an alphabet set. And my letters, they come from my alphabet set. That is why earlier I told you, look here, I have the symbol. I have this tilde symbol over here. This tilde symbol, it doesn't come in my alphabet. It comes nowhere in my alphabet because my alphabet only contain A to Z and A to Z. The tilde doesn't contain. So, I can say this is not a valid word in my language. And even you will have something regarding the construction. For example, you call it grammar. Okay? I cannot write like this a car. The grammar doesn't sound good. I have to write this is a car. So this is what you mean by a formal language. This something which consists of words. If you go for the definition, it is a formal language. It will consist of words whose letters are taken from alphabets and are well formed according to a specific set of rules. The specific set of rules, I call them to be my grammar. So this is what you mean by a formal language. Now let's see how you mathematically define a formal language. Now, languages, they are denoted by a letter called L. So, when you encounter the letter called L, it means you are defining a language. Now, you do have something called symbols, or, I can say they are my letters, symbols or letters. They can be your component line A, B, 1, 2, Z, 0, etc. You call them to be your symbols. Now, alphabets, they are a collection of symbols. They are a finite and non-empty set of symbols. Please have this word into your mind. Alphabets, they are always finite. They can never be infinite, and it should be non-empty. You cannot have a null inside it. You cannot have a null set for alphabet. So alphabets, they are a set of the symbols. I do have my symbols over here, and now I do have a set of symbols over here called the alphabet. Alphabet is always denoted by sigma. So now I do have a set over here called sigma ABC. Now this is my alphabet set of small a, small b, small c, which means when I make a language called L, when I make a language called L, a language is nothing but a set of strings. Now, when I make strings in this language, it can consist only of A, B, and C. Now, if you look down, you'll see something called strings. Strings is nothing but a finite sequence from sigma. Now, in my sigma or in my alphabet, I have only A, B, C, which means, I can have strings only with A, B, C. Now imagine I have a string called A, B, D. In my particular language, A, B, D is not permissible because my sigma contains only A, B, C. So I can have a combination of A, B, and C's. Now look here, I do have another set of alphabet. This is my second set of alphabet. I can have, in this set, I do have only two things. I meant my binary. I do have zeros and ones. Now, the string formed from this particular sigma can be only a combination of zeros and ones. I cannot have something like 0A. Okay, imagine I'm planning to have something called 0A. It will not be permissible because I don't have A over here. Okay, so this is what you mean by a symbol, an alphabet, and a string. A language is nothing but you will have many strings. You will have a many strings, like, I can say, construct a language with all strings which start with A. Okay, for this particular alphabet, I can have a language called have a language where everything starts with A. For this particular alphabet, I can have language. I can have a language, which language is also a set. Have a language where all the strings end in 0, or where all the second character is a 1, or where everything will have 3 digits of 0. You can have any kind of a language, but it must be only from this particular sigma. Now, strings, they can have something called a null. Now, when we talk about formal languages, null is always denoted by epsilon. This is the letter epsilon. Now, epsilon means nothing but null. Okay, a string can contain, it need not always contain, but it can contain a null value. Now, let's see a few things. Okay, now, as you all know, alphabets, they are denoted by sigma. Okay, so I have my first sigma. I just simply called it by a name A over here. This is my second sigma, my third sigma, and my fourth sigma, I gave it sigma itself. Now, we have to find out whether each and every one of these are alphabets. Now, to find out whether each of these are valid set of alphabets, as I told you earlier, you should have this particular definition in mind. Alphabet is nothing but a finite and non-empty set of symbols. So let's find out each and every one. A is equal to 1, 2, DV. You can have any combination. The only thing is, whatever combination you have, you can make up strings only from that particular combination. So I do have a set of sigma A equal to 1, 2, DV. This is a valid set of sigma. Okay, it satisfies two things. It is finite, it is non-empty. Now let's go for the next one. X is equal to AB, and etc. It goes infinite, uncountable, it goes infinite. From the definition, your alphabets cannot have infinity. It should be finite. So my second one, X, it is not a valid set of alphabet. My third one, Y is equal to null. That also, it is an invalid alphabet. Let's go for the last one. Sigma is equal to X, Y, Z. This is also valid. So this is how you find out whether a given set of alphabets are valid or not. It should be finite. It should not contain a null. But strings can contain null. Now let's identify the symbols in each and every one of these alphabets. Now, this A is my set of alphabets. If I go into the symbols or letters, 1 is a symbol, 2 is a symbol, D is a symbol, V is a symbol. I need not talk about this case and this case because they are no longer valid. And the last one I can say X is a symbol, Y is a symbol, and Z is a symbol. Now we'll see something called length of a string. These are things which you know. Now we denote length of a string in this particular notation. Now if I have a string called car, C-A-R, okay, let's say I say S is equal to car. Now the length of car, I denote it in this symbol. Okay, it is enclosed in 2 lines. So, I can say S is S denotes a string called car, and the length of S is nothing but 3. Now, let's find it out. Now, I do have my alphabet sigma is equal to AB, which means I can be making strings only from A and B. So I do have a string over here. Let's first check whether the strings are valid or not. AAA, BB, AA. It contains only A and B, which means very good. The string is valid. The second one is also valid. And the third one is also valid. All these are valid because, they're taken from the alphabet set called AB. Now let us find the length of each. Very simple. The length of this is 3 plus 2, 5 plus 2. This is 7. This is a 3. And this is a 1. So that is about length of a string. Now you do have a very important term called parse of sigma. Now, look over here. Sigma is equal to AB. And let us even go into our previous one. Look here. I told you this, the length is 7. This, the length is 3. And this, the length is 1. Okay. Now let's come back to a parse of sigma. Now, when I write sigma 1, sigma raised to 1, it means that it is the set of all strings over sigma, which has a length of 1. So let's make it very simple. Think about all the possible strings which can be made from this particular sigma, which has a length of 1. So the only possible strings are I can have either A or I can have B. I can think about no other string. So sigma raised to 1 is nothing but A comma B, the set of all strings which have a length of 1. So let's find out sigma raised to 2. Sigma raised to 2 is nothing but sigma, which means, because it is sigma raised to 2, it means nothing. The set of all the possible strings which are possible from sigma AB, which have the length of 2. So let's find out the combination. You can have a string called AA. You can have a string called AB. Then you can even have a string called BA. You can even have another string called BB. Okay, these are the only possible strings which you can have from sigma equal to AB, which has a length of 2. So, I can come up to a very simple conclusion. I have two symbols. I have only two symbols in my sigma, 1 and 2. And if it is sigma raised to 1, I will be getting 2 strings. Okay, here I do have only 2 characters in my sigma, A and B. But I'm talking about a length of 2, which means I will be totally getting 4 strings. Imagine I talk about length 3. Okay, I'll have a combination AAA, ABA, AAB, so on. I can go on writing. I will have a total number of 8 strings. Okay, so again, we can come to a common conclusion telling that, if I have 2 letters in my alphabet and I am planning to have a length of 1, it will be 2 raised to 1. The number of strings will be 2 raised to 1. If I'm having 2 letters in my alphabet, and I want a length of 2, I can say I get total number of strings 2 raised to 2. If I have 2 letters in my alphabet and I need a length of 3, I will be getting a total of 2 raised to 3. I will be getting a total of 2 raised to 3 strings. So imagine you are having I can come to a generalization. Imagine you're having only 2 letters in your sigma. If you want to construct strings which can have length of n, you will be getting 2 raised to n number of strings. So the number of strings which can be obtained from a sigma which has only 2 characters and a length of n is 2 raised to n. Okay, so sigma n, imagine you're talking about sigma n, you will be getting 2 raised to n. Okay, now you're getting 2 raised to n because why? You have only 2 letters over here, isn't it? Now imagine you can have n number of letters. You can have A, B, C, D, E, F, G. Imagine 26 letters. You can say 26 raised to n. Or I can say the total number of strings which can be constructed from a given alphabet is of a given length n is the length of the alphabet, whatever is the length, raised to n. These are the total number or the set of all strings which can be constructed from a given set of alphabet with a length n. Now, you can even make something which has no length. Okay, no length, of course, it will be your null set. Or you can say you will have only one element. Which is your null set. Okay. So now Let's do a quick revision. How many strings are possible with two symbols of length 2? Okay, my sigma I've taken into consideration. Sigma is equal to AB. How many strings are possible with two symbols? Okay, two symbols, length 2. Okay, you know, it is AA, AB, BA, BB. So it's 2 raised to 2, which is 4. How many strings are possible with two symbols of length n? It is 2 raised to n. This also we saw. How many are possible with sigma symbols of length n? So this is something which you need to keep in mind. It always comes as questions for your aptitude test. How many strings are possible for any language which has sigma symbols and a length of n? Now let's go into the most important thing called languages, L. Languages, they're always denoted by a capital letter called L. You simply give L, or you give L1, L2, L3, and then you give any name. But anyway, you normally have that L over there, that letter L. Now, language is nothing but a collection of strings. Now, language also, as we saw earlier, it can happen only on a given set of alphabets. Now, the alphabet which I have in question is sigma is equal to A plus A and B. So these are the only two possible letters in my alphabet. Now, set of all strings with length A, with length 2. Okay, set of all. So I can write L1. This is how I write my language. L1 is equal to, you will open up a curly bracket. And then what is my L1? The set of all strings with length 2. So I can have AA, comma, AB, comma, BA, and BB. I'm not writing everything. So this is my L1. Language 1 is the set of all strings with length 2. Now let's think about another language, L2. Okay, what are they telling me? L2 is nothing but a set of all strings with length 3, which means, you know, I cannot have A, B, and all that. Instead, I'll start with AAA. Okay, the set of all strings with length 3. So I'll have AAA, ABA, BAA, BAB, etc., etc. A total, as we saw earlier, you should have 2 raised to 3 strings. Okay, it will not be infinite. Here you will be having 2 raised to 2. You will be having 2 raised to 2. The second one, you will be having 8. Now let's see. A bit different. The length is not given. The length is not given. In L3, they have not given a length. Instead, all what they've told is set of all strings starting with A. Okay, so you can write A. That is valid. Starts with A. They're not told anything about the length. I can have AB. I can have AA. I can even have AAA. I can have ABBA. I can have AAAAAAAB. Again, I can have ABAA. It goes on and on. They've not told about the length. So, you know, I can say, you know, it is infinite. The third one, it is an infinite language. So when you talk about languages, there are two kinds of languages. You call them finite languages and infinite languages. Finite languages are languages where you will be able to find out how many strings are there. Now, the first one and the second one, L1 and L2, I can say they come under the category called finite languages. I can calculate the total number of strings in it. L3, set of all strings which start with A. I have no control over it. I can go on writing. I say it comes under a category called infinite languages. Let's see a small example. Okay, we'll look into the left side first. Okay, I have a sigma is equal to AB. we did see a set of all strings with length 2, and then we know that it is my L1 is nothing but a set which consists of all my AA, AB, BA, and BB. And I'm planning to check whether AB is valid. Now, how do you check whether AB is valid? Look here. You have AB, isn't it? So how do you check whether AB is valid? You check whether AB is present. You start from the beginning and then you check whether AB is present. I check my first string. No, it doesn't match. Then I check for my second string. Yeah, AB. I do have a match, which means, you know, I can say AB is a valid string. Now let's check whether I have a particular string called BBAB. And then I'm asking, is BBAB a valid string in your language? Your language, it consists only of strings with length 2 with the alphabet A and B. But you know, they're asking your question, is BBAB valid? So what do? Take BBAB, check with the first string. Check with what? Check with AA, not valid. AB, not valid. Then you check with BA, third string, not valid. Fourth string, not valid. You only have 4 strings. You have checked with all the 4 strings, which means, you know, you have come to something called an invalid string. So I can say AB is valid in this particular language. Okay, I have a language over here, L1. AB is valid, while BBAB is not valid. Now let's think about an infinite language. We saw this example earlier. We have AB, all strings starting with A. Okay, you don't have this, okay? I made a mistake. You can't have D over here. Okay. Anyway, you have a set of all strings starting with A. It goes on and on infinity. You have no control over it. The same question. Is AB valid? Yeah. You check with the first one, then you check with the second one, then you check with the third one. Yeah, third one. It is a match, which means, you know, AB is valid. The same technology, the same logic. You start from the first one, go to the second, third, fourth, fifth. You go on checking. Yeah, you get it is valid. Now the same question again. Check whether BBAB is valid. Okay, because you people are humans, you will be able to quickly say it starts with B, but it is just because it starts with B, it is not valid. But you know, as I've always told you, machines, they need instructions. Machines, they cannot very quickly logically think as you people think. So the same logic is followed. Okay, I go on checking with my first string whether BBAB is valid, then my second, then my third, fourth. It goes on and on. I'll have to go on checking infinite number of times, and then only I can be able to tell whether BBAB is a valid string when my language is infinite. So this is how you check whether strings are valid or not. Okay, now we have something called closures. In languages, we do have 2 types of closures. They're called clean closure and positive closure. Clean closure, they are denoted by sigma star. And positive closures, you will denote it with sigma plus. Now, clean closure means it is a big universal set which consists of null set. Okay, this is my null set, which consists of null set together with all my strings of length 1, all my strings of length 2, length 3, etc., etc., all my strings with length n. So very simple. Clean closure is the universal set which consists of all the strings of all possible lengths, starting from my 0 length up till my n length. Very simple. It will be an infinite set. Okay. Now, positive closure means you will not permit the null set. Okay. You don't permit the null set. Instead, it is also a universal set again, but smaller than your clean closure. It will consist of all the strings with length 1, with length 2, with length 3, etc., etc., up till length n. So, you know, if you go for a difference between your clean closure and your positive closure, you will be getting your null set. Okay, so in your clean closure set, you will contain even the null set and all the strings. In positive closure, you will contain all the possible strings except the null. So that is why I very clearly wrote over here. Clean closure, you can allow the null. In positive closure, you cannot allow the null. Now, you might be all wondering why we need formal languages. Now, let us take a very simple example of your Java programming language. Now, look onto the right side of the screen. I've written a small hello world Java program. Okay, public class hello world, public static void main string arguments, SOP, hello world. I do have all my brackets, etc., etc. Anyway, this is a perfect program, no errors. I give it on into my JavaScript compiler. It will be compiled. I will get the result. I will get a hello world printed on my screen. Now, let's see how these compilers work. Now, compilers, they work on these formal languages. Now, when you think about my Java program, I can have something called a sigma. I can have something called a sigma, and that sigma will be all my alphabets starting from A to Z, my A to Z small also. Then I'll have all my symbols like, all these symbols, my comma, my dots, everything. So all that is my sigma. Now, each and every program in my Java, I can consider it to be a string. Okay, each and every program. Now, this hello world Java, I can consider it to be a single string. Okay, now I can have n number of programs, or I can have infinite number of programs, which means, my language, my Java language has infinite number of strings. Okay, don't confuse your normal strings with your formal language string. Now, when I'm talking about a string, I mean I'm talking about a program, because I am considering this whole program to be a string, which means I can have n number of programs. You think about all the programs in the universe, you can say it is an infinite number of programs. Now, imagine I have a small error over here. I know I forgot this bracket over here. It means my program is an error. So if you go back to your earlier case, I do have a string of all the possible programs. I need to check whether a given program is valid or not. So for that, what I do is I will go to my language. As I told you, my language, it will have all the programs. So I will take my particular string in question, start from the beginning. First one, second one, I will go on checking till I reach the last one. In case I do not find a matching string, I will say my program has an error, which means, the user has to do some magic on it so that, I get an error-free program. Now, when you think about this infinite number of programs, it is really impossible to have a language which has all these programs because they are infinite. So what we do is we do a combinatory logic so that, with a particular abstract machine, we will be able to develop all possible programs. Or very simple, you can have something like this. You can have a representation. Let's say I have a small machine over here. I have a small machine over here. I will call it a representation. I just give it a name called representation. I have a language. Okay, I have a language which has all the possible strings. I will be giving a particular input. Let's say I give an input called IP. I should be able to tell whether it is valid or not valid. Now, this particular representation, you call it by the word final automata. So very simple. Final automata is a representation of an abstract machine which will give you a acceptance or rejection for a particular input on a given language L. So this is what I say is an automata or an automaton. Automaton is singular and automata is plural. So I call this to be my automaton.